Now, as I said before, we are going to approximate more sources by what's called a black body. Now, a black body is essentially a representation of reality. It's a nice representation of reality because you can derive analytical expressions and simplify a lot of things and gain intuition. That's the main goal here, not just to derive beautiful math. So all the light sources of interest to us, such as the sun, incandescent lamps, everything can be modeled as black body emitters. Now, also just keep in mind, anything that emits light, by theory, has also to absorb light. This is actually a very interesting point, and we'll come back to this later on. Let me repeat that. Anything that emits light must also be a good absorber of light. In fact, this is not easy to understand, but there is a very important paper that we will actually talk about later on. It says a good solar cell must also be a good light emitting diode. Let me repeat that. A good solar cell, which is absorbing light, must also be a good emitter of light, which is a light emitting diode. This is somewhat counterintuitive, but it all comes from the second law of thermodynamics, and we'll come to that later on. In any case, so when I say black body, it doesn't necessarily just mean something that emits light. Just keep in mind a solar cell can also be a black body. That's all I'm saying for now. An ideal black body absorbs all incident radiation on its surface and emits based upon its temperature. Now, before we look at the equations, let's just zoom in here. So this is an example of a black body radiation. This is spectral irradiance, just like what we saw before. In the lamp, we had those very sharp lines and so on. This is nice and smooth. So it's mathematically kind of easier to handle. So that's why it's an idealization of reality. The horizontal axis is wavelength. And this is the black body radiation of the sun, approximating the black body radiation of the sun. The surface of the sun is approximated at 6,000 Kelvin. And the plot that shows 6,000 Kelvin, this is what we expect to see if we represented the sun by a black body on Earth. Okay, so you can see most of the peak is in the visible, right? In fact, you can see this is around the yellow wavelength, the peak, and this is the reason why if the sensitivity of our eyes peaks also at the same wavelength. Because we are daytime creatures. We have evolved over millions of years such that our the cells in our eyes that respond to light are most sensitive to the peak wavelength from the sun. Of course, different animals have different responses because they have different activities, I suppose. The other thing I should point out is that you can see if you look at different curves at different temperatures, so this is 6,000 Kelvin. If you look at 4,000 Kelvin, the peak has dropped down here. Two things have happened. The peak value here has dropped dramatically, has gone down from here to here. The second thing that has happened is that the wavelength has shifted. So here it was in the yellow. This has gone into the infrared. So the color of the source has changed. Okay. Now it turns out these are normalized plots. If you do an integral, the area under these curves, they are conserved, but not terribly important for our discussion here. Oops. Now let's come back to some simple math here. So the spectral irradiance is governed by Planck's radiation law. In fact, this is the starting point of quantum mechanics. The black body radiation allowed Planck to essentially quantize the electromagnetic field and define what a photon is. You don't need to know any of this. In fact, you don't need to memorize anything, by the way, in this class because all the exams are open book. But I want you to get intuition. If you look at this equation, all this says is how does the power emitted by a black body change with spectrum and temperature? Temperature we'll focus on. So with spectrum, it's a complicated equation, but it's a nice equation to differentiate and integrate. So from that perspective, it's a nice equation. And this equation represents these plots here at different temperatures. T is the temperature of the black body in Kelvin. Okay? Now, the total power density, as we know in the previous slide, is simply an integral of the whole thing, 0 to infinity. And that gets a very simple equation called the Stefan Boltzmann law. So that's why this is kind of beautiful, because this complicated stuff, which, by the way, comes from statistical mechanics. So it's a probabilistic thing. Anyway, so there's some interesting beauty there. But once you integrate it, you get something very simple like this called the Stefan Boltzmann law, where all it says is that total power density coming out of the source is proportional to the fourth power temperature. That's a pretty incredible dependence if you think about it. Fourth power temperature is highly nonlinear. So in other words, I go from 100 degrees to 200 degrees. I'm increasing the total power density by 10 to the 8. It's a crazy thing, right? That those things don't exist in nature. So it's kind of a very interesting, beautiful thing. Of course, sigma, which is a Stefan Boltzmann constant, is a very small number, 5.67 10 to the minus 8. Units, yeah, I'm obsessed with units here, but we should check all the units, right? So this is joules per second per meters per Kelvin raised to 4. You multiply it by temperature raised to 4, which is Kelvin raised to 4. This thing disappears. So you end up with joules per second per meter squared, which is nothing other than watts per meter squared. So everything again is consistent. That's what H is. We've seen this in the last few slides. Okay, good. Far so good. Now, putting all this together, we can also determine the wavelength where the spectral irradiance is maximum. In other words, this point here, and this point here, and this point here, and this point here. You see this curve, which maps the peak wavelength where the spectral intensity is maximum. Of course, from calculus, we know in order to do that, this is very simple. You take this equation and you simply take the derivative with respect to lambda and set that to 0. And you take the second derivative and make sure it's less than 0. Right? We all know this from simple calculus. And this equation is actually pretty simple to actually do this. If you're interested, I encourage you to do it. You end up with a very simple expression shown here. Some constant divided by T. This is also called the Wien's law. Now that constant is 2900 if we measure the wavelength in micrometers and temperatures in Kelvin. And what does that mean? That means the hotter the black body, the peak wavelength is shorter, right? Lambda is inversely proportional to temperature. So if you look at your campfire, if it's white versus if it's red, what is hotter? I think many of you are probably avid campers, more avid than me, but go ahead. Yes, I would say the white, because white is kind of a mixture of blue and green and red. Red is more just red. Or blue when you cook. Yeah, you see the blue flame. What does? Steel, okay. Yeah, I'm not familiar, but yeah, exactly the same reason, yeah. But cooking is the other example to think about. So I have a simple question here. So that just to summarize, the temperature of the black body affects both the spectral distribution, so that shape we saw, remember, it get flattened as the temperature went down, but also the total power density, that integral also matters, right? Depends on temperature by the Stefan Boltzmann law. So if you look at this picture here, I don't know if you can see this. If you're an astronomer, you can look at this picture and say, oh, which star is hotter? Betelgeuse up there, now Rigel at the bottom. And now I think all of you know which one's hotter. Yeah, I mean, it's okay to make mistakes, but I make them all the time. Hotter. Which one's hotter between Betelgeuse or Rigel? Oh, sorry, can you not? This or this? Yeah, Rigel will be hotter. Just from the color. So just a very simple kind of a toy problem, right? You can imagine if in the old days, the astronomers, once you knew this, you could look at the color and figure this out. And even today, people do this to some extent. In fact, some of the missile defense systems used to, I don't know if you're familiar with I forget what it's called, but there's a missile defense system in Israel, which is quite famous. It shoots down any missiles that come in, and that uses kind of a heat signature, but the heat signature is based on a spectral content. There's a camera that tries to detect the spectral content and tries to, because the plume of missiles have a specific spectral content, the spectrum, the plume of a rocket is a black body, and that is a specific spectral content, and you can track it very precisely and separate it from decoys and things like that. It's a very, very important thing in missile defense. It also makes missile defense a very challenging problem, by the way. I mean, of course, you can think of many other applications. It's just an example. Okay, now let's try to, oh, I have to go a little faster. Let's try to understand some of the basic physics of what's happening in the sun. Again, this is really for intuitive purposes, not, you don't need to memorize any of this. The sun is essentially a plasma. What is plasma? Plasma is a form of matter, which is neither liquid nor gas. So it's kind of a mixture between them because it's so hot. Everything is ionized. Nothing, at least in the very interior, there are no atoms because it's too hot. It's ionized. All the electrons have too much kinetic energy to be stuck to the nucleus, essentially. They're all over the place. So the sun is a hot sphere whose internal temperature reaches over 20 million Kelvin due to nuclear reactions in its core, which convert hydrogen to helium. So of course, I mean, very, very simple physics is that you have huge amounts of pressure, very high temperature. Hydrogen atoms fuse together, undergo nuclear fusion under these extreme conditions, form helium. This process releases huge amounts of energy, nuclear fusion. And that energy is what we see here. And that gets transmitted from the inside. So at the very, very inside, you have the inner core. There is a transmission of energy using, there's a radiative zone, so radiation, and there's a convective zone, this plasma essentially circulates. And then it heats up the surface of the sun, which is also called the photosphere. And it's approximately 6,000 Kelvin. So it goes from about 20 million Kelvin in the interior to about 6,000 Kelvin at the surface. Keep in mind that the sun is huge, right? About, I don't remember how many times larger than the Earth, but it's tremendous. It's huge. Yeah, the surface area is, yeah, I have the number somewhere anyway. So this radiation is what we see here. So on Earth. So the temperature of the surface of the photosphere is about 6,000 Kelvin. So we can say the solar spectral radiance approximately resembles a black body at 6,000 Kelvin. So that's the reason for that. And the total power emitted by the sun is the power density from the sun from a black body of 6,000 Kelvin multiplied by the surface area of the sun. And that turns out to be a pretty huge number, 9.5 times 10 to the 25 watts. Okay, so that's the total total energy coming out everywhere from the sun. So if I were to think about the sun as a point source, it's simply emitting in all directions, right? Going outward. Like that. Now, once it goes out into space, as I drew here, let me just draw my point again. This is simply escaping farther and farther away. The power, the total power is the same, right? You're not getting more power, but it's getting spread over a larger area. So power density is going down with distance, as expected. The total power is the same. I'm spreading it over a larger surface area. Power divided by area is power density. So my H, watts per meter square, is decreasing. That's obvious. Mars or Mercury is much hotter than Pluto or Earth. So the distance from the sun matters, right? So, and it's easy to scale it. So we can use this simple expression. If we have if you have a planet at some distance d from the sun, we can scale it as shown here. The total power density, not total power density, average power density is sigma T raised to 4, which is Blackbody total power coming out of that source, times the area, that's the total power density coming out of that source, multiplied by the surface area of the sun, 4 pi r squared sun, which is the top thing. And then the bottom thing is divided by the area over which the energy is spread, 4 pi d squared, capital D squared, which is the distance. So it's simply the ratio of the radius of the sun divided by the distance from the sun squared. A simple scaling. So if you do this, Venus gets something like 2,611 watts per meter squared. Earth gets something like 1366 watts per meter squared. But Pluto gets a very small fraction, of that 0.878 watts per meter squared. Makes sense because it's farther away. Now, these are idealized numbers. Of course, when we say 1366, this is an average, right? Not necessarily what you will measure, but it's got to be approximately on a good direct sunny day is what we see. The actual power density also changes as the Earth moves around the sun. So for example, in January, the Earth is closest to the sun, you would expect more intensity. In July or so, it is farthest from the sun, you'll expect less. And there are, of course, the different changes as you go along. And you can model this fairly carefully as shown by that equation. Again, we won't worry too much about this level of detail at this point, but something you should be aware of. Now, for the purposes of building solar cells, testing solar cells, or building other absorbers, we have to have standards because we can't just say, oh, it's this black body, and you can't just measure it in one location. If you measure it in Boston versus you measure it in Salt Lake City, they'll be very different. So you want to have standards if you want to compare the solar cells from one manufacturer to another. So there are standards. They're called AM 1.5 global, and we'll explain what that means shortly. AM 1.5 direct and AM 0. AM 0 represents the solar insolation in space. So if you're building solar panels for a satellite, that's what you would use. That's shown in the red there. So of course it's high. After it passes through the atmosphere, you lost some of the light. So that's what you see in the blue. Global refers to scattered light plus direct light. Of course, the atmosphere will scatter some of the light. Not everything passes straight through, right? Otherwise, the sky won't be blue. We'll come back to that. And AM 1.5 direct means whatever is coming direct. Now, the difference between direct and global is important because global light, direct light, in order to capture it, for instance, with the solar concentrator, you have to track the sun because the angle is important. Whereas a diffuse light, which is global, direct plus diffuse is global. The diffuse light comes from everywhere, all kinds of angles, and that's harder to capture. We'll see this again next week. But just be aware of these things. I'm gonna go a little faster again, feel free to go back and read it. Not terribly important, but we are all aware that the atmosphere absorbs and scatters light. So for instance, if I think about light coming in as 100%, about 15% of the light, 18% of the lights are actually absorbed in the atmosphere by dust, water vapor, oxygen, nitrogen, and so on and so forth. About 3% is scattered back into space, re-emitted and scattered, and about 7% is scattered to Earth. What does that mean? That means some of the light, instead of going straight through, gets scattered in all directions. It might scatter back to Earth as well. So what you end up collecting direct to Earth is about 70%. That's what comes unscattered. And then about 7% that comes diffuse. So on a perfect cloudless day, if you go out, compared to what you can see on space, you're getting about 70% direct and about 7% from the rest of the fact that the sky is blue. That's also photons coming to you, right? That's about 7% of the light. So keep that in mind. Of course, this depends also on seasonal variation, things like the fact that we have smoke, pollution, clouds, whatever. So also just keep in mind that this, of course, varies with seasons, as we all know. When we are facing the sun in the summer versus away from the sun in the winter, the latitude, these things are important because of the angle that the sun makes with the earth, right? And we'll see this again and again. So typically when we design systems, we want to consider the entire operating time, like an annual energy production or something like that. So keep that in mind when you work on your projects. Not only the power, here we only talked about power, the spectrum of light can also change. So keep in mind that the spectral content can change as well, because some wavelengths scatter more than other wavelengths. This is the reason why the sky is blue, because blue, the short wavelengths from the sun, are scattered, and they come to our eye from scattering from the atmosphere. If you look straight at the sun, it's white, because all the light comes through, or red if it's cloudy, because the reds are scattered less. Okay. Anyway, these things are relatively straightforward. So atmospheric effects, there are many effects we should be aware of, things like absorption in ozone, carbon dioxide, water vapor. Lots of the long wavelengths are absorbed by water vapor and carbon dioxide. Most of the UVs absorbed by ozone, which is a good thing, otherwise we'll all be dead. But of course, not enough ozone, not enough to prevent sunburn, so it's something we should be aware of. You also notice that if I go back to this spectrum, you can see these really, really sharp tips here. These things look unnatural, right? Why are they so discontinuous? This is because you get absorption because of molecular resonances. So there's water vapor absorbs light and it's resonating. And there's a particular resonance that when I'm doing this, I mean the molecules are moving. And when they absorb a photon, they move in a slightly different way. And that absorption happens at a very narrow band. This is like a laser, essentially. So that's why you actually end up seeing these things. And there are many of these, right? All kinds of molecules do this kind of stuff. Then, whoops, am I out of time? Oh, okay, we have a few more minutes. But I guess I should speed up. Yeah, direct versus diffuse, I already talked about it. If you have a solar concentrator, you particularly only collect direct light, so you have to track the sun. Diffuse light is very hard to collect. For instance, with concentrate, we'll talk about this next week in a bit more detail. Air mass. So I told you before the notation AM in the standard refers to air mass. AM 1.5 refers to the standard that's used that represents this distance, traveled by the sun. And this is theta. This distance is called the air mass. And this goes as 1 over cos theta. And that's equal to 1.5. That is what's called the standard. So it's not exactly overhead, but some angle in between. Actually, I don't remember what it is. 2 or 3, so something like 35 degrees or something like that, I guess. But anyway, the intensity, of course, depends on that angle, because the more atmosphere you pass through, you get more absorption and scattering. So during sunset, you have the most atmosphere passing through, so you get very little light, so it doesn't feel as hot as it would when it's under noon. And of course, the color is also different, right? Sunset's more like red because the blues have been scattered away. Whereas overhead, there's less scattering, so you see more of the light. So these things are things we should be aware of. Oh, good. Okay, so I'm on time. That's the last slide. I just wanted to make sure everyone was clear about the presentation one. So just to summarize, before I talk about this, from today's class, I want you to just review and understand the intuition about spectrum, power density, and some basic ideas of sunlight. These things are important when you start designing things next week and in your projects. So we'll kind of hopefully gain some basic intuition and build up on it. That's my hope. Now, okay, presentation one is going to be on Thursday in class. So for those of you who are taking the in-person portion of the class, please be here, except for one team. who will be doing hybrid. It's about 10 minutes. Keep it as clear as possible. About 5 minutes of Q&A. Everyone's encouraged to ask questions. I'll ask mostly, probably, but feel free to ask. Again, this is not to put your colleagues on the spot. It's really for all of us to learn and help you with your project. I'm not going to penalize you because you don't know the answer. I want to make sure you think through the things, okay? These things. Again, just remind yourself, the goal is to become intimately familiar with the topic so you know how to innovate, what problem to solve, okay? Other stuff I think is okay. So what are the main product solutions that exist today? What are the main challenges generally in this field? Compare advantages and disadvantages of existing products and solutions to as much detail as possible with references and so on. Yeah, I think the rest is okay. You don't, if you want, you can submit the slides. You don't have to. You will submit